How did ancient humans make glue before chemistry existed? Imagine holding a razor-sharp stone point in one hand and a wooden shaft in the other. Each piece works by itself, but together they could become something far more useful. A spear, a knife, a scraper with a handle. There is only one problem. Stone does not naturally stay attached to wood. A strip of hide can bind the pieces, but the joint can twist, slide, or loosen under force. To make a reliable composite tool, ancient humans needed something sticky, strong, and controllable. In other words, they needed glue. That sounds almost absurdly modern. Glue feels like a product of factories, bottles, polymers, and chemistry labs. But the oldest known adhesive technology reaches back at least 190,000 years. Long before anyone knew what a molecule was, hominins were already changing natural materials with heat and eventually combining ingredients to make substances behave differently. If you enjoy stories where a familiar technology turns out to be far older than it looks, subscribe to Ancestral Brain. The first important thing to understand is that prehistoric glue was not one invention. Different groups in different environments used different sticky materials. Natural bitumen can seep from the ground. Some trees produce resin or gum. Beeswax can modify other substances. And birch bark can be transformed into a dark tar. What connects these materials is not a single recipe, but a problem. How do you make separate parts act like one tool? One of the earliest known answers comes from Campitello Quarry in Italy. Stone flakes found there carried birch bark pitch, and the archaeological context places them at least 190,000 years ago. That is extraordinary because birch bark is not simply sticky in the way fresh tree resin can be. To obtain useful tar, the bark has to be heated so that its organic compounds break down and a sticky material can be collected. And this is where the story becomes more interesting than the word glue suggests. You do not need pottery, metal, a thermometer, or a sealed laboratory vessel to make birch tar. Experimental archaeologists have produced it using materials available in the Paleolithic. Birch bark can be heated under restricted oxygen, and tar can be collected as volatile products condense. Experiments have also shown that relatively simple setups can produce usable amounts. But there is a major scientific limit here. Archaeologists can identify ancient birch tar. They cannot watch the person who made it. Several production methods are possible, and researchers still debate which techniques were actually used at particular Paleolithic sites.
So both are necessary.
A lump of tar proves that the material existed. It does not automatically reveal every step of the recipe or the exact cognitive demands involved in making it. That distinction matters because prehistoric adhesives are often turned into arguments about intelligence. What the evidence establishes more securely is that Neanderthals did use adhesive technology. A roughly 50,000-year-old flint tool recovered from deposits now beneath the North Sea preserves birch tar associated with hafting. Other European sites have produced conifer resin on Neanderthal tools, including one case where resin was mixed with beeswax. In the Caucasus, researchers have identified bitumen on Middle Paleolithic tools associated with Neanderthals. So the old picture of Neanderthals simply gripping crude stones in their bare hands does not survive the evidence. They were assembling composite tools from materials with very different properties. Stone for a cutting edge, wood or another material for a handle or shaft, binding when needed, and adhesive to stabilize the connection. Think about what that changes mechanically. A sharp flake is useful, but a handle lets force be applied differently. A point fixed to a shaft can become part of a hunting weapon. Adhesive can stabilize the joint between uneven surfaces and work together with bindings to keep components in position. The important innovation was not glue by itself. It was learning that a tool could be designed as a system. And ancient tool makers did not rely on one kind of chemistry everywhere. In parts of the Middle East and the Caucasus, natural bitumen provided another solution. Unlike birch tar, Bitumen can occur naturally as a sticky petroleum-derived material. People could collect it and use it for hafting, sometimes modifying or combining it with other substances. In central Italy, chemical analysis of residues on Neanderthal tools identified conifer resin, and one sample contained resin mixed with beeswax. That mixture reveals an important principle. Sometimes the best adhesive is not simply the stickiest substance you can find. An adhesive also has to be workable. It cannot be so brittle that it cracks immediately, so fluid that it escapes the joint, or so difficult to handle that assembling the tool becomes impractical. Changing ingredients can change those properties. We see an especially striking version of this in southern Africa. At Sibidu Cave, evidence associated with Middle Stone Age tools, more than 70,000 years old, indicates compound adhesives involving plant gum and red ochre. Experimental replication showed that adding ochre could change how the gum adhesive performed, and that drying and heating the mixture required control if the adhesive was going to remain useful. That does not mean every red stain on a stone tool is automatically proof of a sophisticated glue recipe. Organic residues decay, contamination is possible, and researchers often have to combine chemical analysis, microscopy, wear patterns, archaeological context, and experimental replication. Prehistoric glue is difficult to study precisely because so much of the evidence can disappear. The evidence that survives is probably only a fraction of what once existed. Wood rots, plant fibers vanish, handles decay, thin films of gum or resin can degrade beyond recognition. Stone survives much better, which creates a strange bias. Museums can fill rooms with stone points while the organic materials that once made some of those points, parts of functioning composite tools, are mostly gone. The irony is that modern chemistry is now one of the tools archaeologists use to recognize this ancient chemistry. Tiny residues can preserve molecular signatures that help identify materials such as conifer resin, birch tar, or bitumen. Microscopic wear can reveal where a stone tool rubbed against a handle or binding. Neither line of evidence answers every question by itself, but together they can expose parts of a technological system that would otherwise have vanished. So how did ancient humans discover any of this without chemistry? Probably not by understanding molecules, by understanding materials. Imagine resin oozing from a damaged tree. It sticks to fingers, dirt, bark, and stone. That property can be observed directly. Warm it, and its consistency changes. Let it cool, and it changes again. Combine sticky materials with other ingredients, and the result may behave differently. None of that requires a theory of polymers. It requires observation, memory, repeated trials, and comparison between results. Birch tar presents a harder puzzle because the useful adhesive is not simply waiting on the outside of the tree. Heating transforms the bark. How people first encountered that transformation is unknown. Perhaps tar-like material was noticed during repeated encounters between birch bark and fire. Perhaps deliberate production developed through another path entirely. Archaeology cannot recover the first experiment, so any tidy story about the original inventor would be speculation. But once a useful process existed, it could be reproduced and transmitted. Collect this material, prepare it this way, heat it until it behaves correctly. Apply it to this part of the tool. Warm it again if it becomes too stiff. Combine it with another substance if the mixture works better that way. A person can learn an effective sequence without knowing the chemical explanation behind a single step.
Perfect.
That is the deeper answer to the question. Chemistry existed long before the science of chemistry. Heating birch bark transforms organic material. Drying plant gum removes water. Mixing mineral powder into an adhesive can change its physical behaviour. Warming resin changes how easily it flows and can be worked. Ancient craftspeople did not need the modern vocabulary because they could observe cause and effect directly. And adhesive technology had consequences far beyond making something stick. Once different materials can be joined reliably, design possibilities multiply. A stone edge no longer has to fit comfortably in the hand. A point can be optimized for one job, while a separate shaft provides reach. Small cutting elements can become components of larger tools. Materials with completely different properties can be combined so that each performs the task it does best. That is one of the quiet revolutions of human technology. Not just shaping objects, but combining them. The most revealing prehistoric glue is therefore not merely a primitive version of something in a modern bottle. It preserves evidence of people learning how materials behaved. Across different times and places, hominins used naturally sticky substances, transformed bark with heat, collected bitumen, worked with tree resins, and produced compound adhesives. The exact recipes were not universal, and the archaeological record does not preserve a single straight line from one inventor to everyone who came later. For those techniques to persist, successful procedures had to be reproduced and transmitted. They did not need equations to do chemistry. They needed a problem, materials that could solve it, and enough accumulated knowledge to make the solution work again. A stone point, a wooden shaft, and a smear of dark adhesive may look simple after 200,000 years. But once those separate materials were joined, the tool was no longer just stone or wood. It was a technology made from relationships between materials,